Yeah, I think we can get started. So hello, everybody. Thanks for joining another MLBoost seminar. Big thank you to Chen for agreeing to present for us. The seminar is scheduled to be for 1 hour, but we can go over time if necessary. The recording will be available on the MLBoost YouTube channel. You can also access the slides on MLBoost Slack channel and use that Slack channel for any follow-up questions that you may have on this topic or for discussions with your peers. You are more than welcome to ask questions during the presentation, and I hope you do that so we can have a more engaging conversation. If you prefer, you can also type your questions in the chat, and I will make sure to address them with our presenter. With that, Chen, thank you again, and you can start when you are ready.
Yeah, thank you, Maddie, so much for the invitation. Let me just share the screen, and then let's see if that's, 1 second. Is that small, or should I make it larger?
I think if you can do full screen, that would be better, but if not, it's also
okay.
Yes, this is
better?
Yeah.
1 second, let me make it even larger. Okay, maybe this is okay. Okay. Probably I'll just use this version. And then indeed, feel free to ask me questions during the presentation. And I don't think I can see everyone, so just speak up. And Maddie, it will be great if you moderate as well, like
Sure.
the chat if some question. So yeah, the title of my talk today is called Enhancing Conformal Prediction for Time Series. And the last year I gave near the end of last year, I gave a similar talk based on the slide to the TAFS seminar. And this year I just added more because we have additional work and I think some new perspective as well. And this work is advised by my PhD advisor, Professor 𝚤𝚤𝚗𝚗 at ISYE. And I'm now a PhD there as well. Oops, sorry. So additionally, before I start, I do want to emphasize that the talk is based on several work we had, and they are in chronological order. So the first work is called EMBPI, and I think maybe a lot of you have seen that. So that work had its own conference version and a journal version. And then the second bullet shows the work called SPICY, which is last year. And I think that work improved upon MBPI by a lot, especially empirically. And this year, we had another extension of SPICY to a multidimensional time series. And there is called multi-dim SPICY, and I will also cover that as well. So the outline is I want to motivate because although a lot of us may already know conformal, I do think it's important to view it like why we care about this, because I think a lot of hype nowadays about this type of method. And then I will emphasize what is our goal in our work, because conformal prediction in itself has been applied to many different situations. And in our case, we want to specialize it to our problem. And then I will give a warm-up example as well as covering conformal prediction for IID and for time series, which is the focus of my talk. Then I will conclude. I will give numerical results as well as extensions and conclusions. So because the talk will cover many different work, some of them are not discussed in depth. So that's why I'm happy to talk more or provide link to these papers. So essentially, the motivation is that we know forecasting is everywhere, meaning that suppose I have a black box model that predicts the return or anything that we desire to be 5%. And however, we naturally know that there is uncertainty in the prediction, meaning you either have low signal to noise ratio or you have high variance in your data collection, or just due to your model fitting. For example, due to the first order method, when you train your model, you can have very different predictor if you have different initialization, all of those. So all of them can cause uncertainty. And therefore, the key question in general is how can we quantify the uncertainty? And one way is to say, can we say with high probability what the true return will be? Because I predict to be 5%, but then the ground truth can be something else. So what that is going to lie, where that is going to lie is a key question. So essentially, in our case, we are specializing this UQ problem for forecasting in a forecasting case. And specifically, we assume we have data xi, yi, and this xi are just any feature you have, for example, the past of your history or anything that can help you. And the y now is a univariate response. But in this work, I will also cover the case when it is multivariate, meaning you have multiple values at different, for example, location or any other measurements that you want. And specifically, maybe many of you have seen that, is we want to give in a significance level alpha between 0 and 1, and now a new feature xj. We want to produce a prediction interval, or in general, a prediction set, C, centered where the C depends on your feature, and of course, the significance level, so that the probability that your actual yj. So remember this yj before you actually observe it, your natural before you construct this interval is not known, and the probability of this yj in the interval or this region is at least 1 minus alpha. So this is the theoretical guarantee we want. And for example, more concretely is that suppose this alpha is 0.05, then we're saying with 95% probability, we want this interval to contain the true stock price, because suppose we are predicting the price with this probability. So this is the more concrete example of how you're using or how you're interpreting this C. And additionally, this is generalized to confidence region when you have multivariate output, and I will cover them as well. So before I go to conformal, I do want to highlight a warm-up example, which I think is important to understand why conformal is helpful or useful. So first, suppose you have IID data, xi and y, and you have a simple linear model, meaning that your y is just x transpose beta for some unknown beta plus a IID noise from 0 and 1. And then, because this is I think the first thing people learn in stat course, we know the predictor y hat j giving any new feature, as well as the exact form of the confidence interval. Of course, in finite sample, you have errors, but you can easily bound everything. And that this interval is centered at your predictor plus or minus the t statistics times the standard error. So this is well known for a long time. However, there are indeed several things that I want to point out. So the first is that we do have, when you are assuming these, you are implicitly assuming the linear relationship between your x and y. And therefore, you also know the distribution of y because you know the distribution of the noise. And the second is that when you are predicting a future y, you assume you have no model misspecification, meaning you assume your y is linearly related to your x, but if not, then this is not a valid confidence interval as well. And the last is, of course, we assume the data are independent. So that's another limitation. And therefore, I think in red is the interesting thing that conformal tries to address, which is, can we have something that tries to circumvent this limitation? And indeed, conformal prediction can address 1 and 2, meaning it does not need to know the distribution, and also it's model agnostic. And also, in addition, in our work, we try to further apply or modify conformal prediction when data are not independent, such as for time series. And conformal prediction, especially in a nutshell or for IID data, are just first, you define this conformity score or non-conformity score. For univariate, you can view it as the residual. And then this interval in 1 essentially contain all the, so given a specific feature, this confidence interval or region contain all the y such that your score that you define is less than or equal to the 1 minus alpha quantile on a calibration set, on a score that is computed on a calibration set. So essentially, this is in a nutshell what CP does. And as I said, this equation y includes all the y with scores conforming to the path. And I think that is the reason why it is giving this class of method is viewed as conformal prediction. And also the idea, just want to emphasize, is originated in this work 2007, and there have been quite extensive developments. And there are more comprehensive review in this work in 2023. And just to highlight, this word might need to be modified because they're in general not necessarily interval, but just a set. But nevertheless, the sets that we obtain using equation 1 are first distribution free, meaning you don't need to assume what your conditional distribution of y given x is. And second is you don't need to place assumption on what predictor you're giving, meaning that you can have your own predictor, but then wrap this conformal in a post-processing way on top of your predictor. And the third is that when your data are under some assumption, you can have valid coverage, meaning this interval indeed or this set indeed contains your actual y with at least 1 minus alpha probability marginally. So I would emphasize that there is one main limitation, which is the dependency assumption on the data. So conformal prediction, or at least in its early stages, it requires your data to be exchangeable. For example, IID. So essentially what it's saying is that suppose you have a sequence of random variable, and there is a permutation of the indices. Then the joint distribution of your original sequence is the same as any permutation to your indices. So meaning suppose you just have two, you have Z1 and Z2, then this joint distribution is the same as Z2 comma Z1. And of course, this assumption in itself is less, it's weaker than IID. But however, this is rare for time series because of the strong serial correlation. For example, I know tomorrow's temperature is positively correlated. Well, I know tomorrow's temperature is definitely higher than today. Then this probability cannot be easily swapped when you have a certain pair of values that you want to consider probability on. So, and in this plot, what we're showing is essentially the histogram of the nonconformity score as well as the partial autocorrelation. So here you can see, especially on the right, is that this lag, this PACF decays very slowly with respect to lag, meaning between pairs or residuals or nonconformity score with different lag, their autocorrelation can still be significant or significantly high when they are far apart. So that is why it's not reasonable to assume your the data are exchangeable when you're when you're considering time series. So therefore, how to extend CP in the more general setting is a key and relatively new, but I do think there are a lot of developments so far. So some concurrent work, and again, this is not an exhaustive list because there are definitely more and more work coming, but I think two main threads are first, adaptively adjust your significance level based on coverage or not. And there are several related work in 2021, 2022, and definitely now. And the second type of work I think is also very interesting is you try to reweight, because here, this notation refers to the empirical 1 minus alpha quantile of the score. But however, people have found that if you reweight, not placing one, suppose your calibration set has size n, if you don't place 1 over n weight on each of your calibration sample, but rather weight them based on different scheme, there you can actually address the coverage issue besides IID data. And there are several works on those. And in particular, so when we first have EMBPI, so that's in 2021, that was the time when we, so at that time, there hasn't been much work on conformal for time series. So that's why I say our work is one of the first to understand the problem. And I do want to emphasize we're not in conflict with this work, meaning that you can indeed combine technique for specific application you want. And also in retrospect, our method, especially the more recent ones, they are a type of reweighting scheme. Implicitly, can be implicitly understood as a type of reweighting scheme. And if you're interested, you can look at this 2023 paper by Barbara et al. They actually consider the very general setting of conformal beyond exchangeability. And they say the weighting scheme is one of the, well, they provide a weighting scheme that is guaranteed to help you alleviate the coverage gap. And I think that's why the weighting scheme is one of the very promising direction of handling data beyond exchangeability. So I want to then quickly go through several of the solutions that we have. So this initial solution called EMBPI is as follows. So we consider time series data where your feature can, for example, be the past D value of your univariate time series and or contain other feature that is helpful for your prediction. And then we had an earlier work in 2020 where instead of just having a single predictor, we're building an ensemble model so that we don't need additional holdout sets when you're computing the nonconformity score. So that's why when we are building MBPI, we essentially build upon this work, but with several differences. And equation one is essentially, in a nutshell, what we do. So suppose we still have residual as the conformity score, then your interval is centered at this predictor. So this predictor, again, is an ensemble method that I don't want to go through the detail because they are more notation heavy, but just understood that this is some ensemble. And then your residual are no longer just 1 minus alpha, but we try to minimize the interval width with certain beta that is empirically found by grid search. And then additionally, we are no longer just considering a single holdout set, but rather we are updating the set of nonconformity score in a rolling fashion, meaning suppose I observe new data, Y, and then I'm going to collect new residual or new conformity score to append or update my set of residuals so far.
Sorry, just one question here for to make sure. Epsilon hat here is there. Epsilon hat is the error, not the absolute error, right?
Which one? Yes, it's not the absolute error. Yeah, it's not the
just
absolute
the error itself. Okay.
Yeah, yeah. And one reason for that is actually, if you go back, I actually plotted the histogram of residuals. So these residuals are not absolute, and you can see they're asymmetric. So of course you can take the absolute value, but there I think it will make your interval wider than necessary, and that's what we found as well in reality.
Okay.
Yeah.
Right.
So we don't need, because sometimes we can have either underestimation or overestimation. Of course, if you take absolute value, you can account for both, but that might not be the most efficient understanding the context of narrow interval. So yeah, but that's a good question. Yeah, we're not taking absolute value here, but of course, it's you can do that. Yeah, and additionally, we can show that this interval in one. So in this case, we're indeed building interval because of the design. And we can show that when you have infinite sample or asymptotically, we can have this coverage. But however, there are some limitations, meaning we do have to assume a specific form of your Y given your feature X. So this F you can has a very relaxed choice, and this error is not you don't need to be IID or you don't need to know the distribution, but still you need to assume a specific form of your Y given X. So that's some of the limitation that we had in the earlier work. And additionally, you can find the details of, for example, how to train the ensemble and how we actually work in these two works below. And then I want to highlight additional or the latest solution that we have had, which is called SPICY. So what this is doing is that we realize, okay, we can just take or mimic existing conformal by taking the empirical quantile. However, as we see here, which is the figure I showed previously, the autocorrelation between all your nonconformity score or the residual, they decay very slowly. And in fact, if you use empirical quantile, just go back to the previous slide, which is this Q here, we can actually show this is not a good way to understand the distribution of your quantile of your residuals. And the details is more formalized in the work, but I'm just explaining this in Word. So that's why what we are doing is that instead of having a single quantile, so I'm purposely making everything almost the same as before, except for the part we changing SPICY. So what we do is you can understand this calligraphic Q as not the empirical quantile anymore, but rather is a quantile regression model that is fitted on the residuals. So what I mean here is that given a set of past residual, I'm not just taking the empirical quantile, but apply another quantile regression model so that I can predict the future quantile given any significance level alpha. So additionally, and the next slide I will explain this concept more clearly. But additionally, we are doing this adaptively, meaning that suppose at the first time index we apply this quantile regression, and the second time index or future index you can apply it again, so that we can adaptively re-estimate the quantile. So that's, in a nutshell, the main difference between SPICY and MBPI, where, of course, if you take this calligraphic Q to be the empirical quantile, then these two methods are identical. So that's why SPICY is also a generalization of the MBPI as well. And additional detail can be found in our 2023 work. So I do want to emphasize a few design choice, because in general, you can have many different choices of this quantile regression estimator. And indeed, I will show in the extension part that what we are actively considering as this Q-hat. But in SPICY, when it was published, we were using this quantile random forest. And the reason we use it is because of its efficiency in training. Because empirically, we need to train it on multiple significance levels sometimes. And there, we don't the design of QRF allows us to do that without retraining everything. And additionally, we also provide approved asymptotic conditional coverage of equation 1. And I want to point out that here we are no longer assuming the specific form of y given x. So if we go back, in the previous MBPI, we assume y is a linear, is some function of x plus this noise. But in the later work, SPICY, we relax this assumption. So it's more like a model-agnostic view of how CP is working in this context. And of course, in neither of this work did we assume distribution. So we never need to know what your distribution of y is given x.
Sorry, another question.
Yeah.
With the ENBPI, this dependence of y on x that you just showed, does that mean that does it mean that the dependence of y on the features should not depend on time? Is that what this assumption means?
In fact, you can, meaning that your x can include both time and your original feature. So that's allowed. So indeed, we actually did experiments. So that's a good point. So what we did is this xi. So xi can be the history, like in an autoregressive fashion. And additionally, it can include a time component. So we did experiment there, and it worked as well.
Okay.
It's more like for example, if you have a general fashion of f bracket x comma epsilon, then it's likely to be different from this fx plus epsilon, because the noise can enter into your time series in a very complicated way. But here we only allow it to enter linearly.
All right.
Yeah.
And then this other question, you said asymptotic conditional coverage.
Yeah.
I think you also mentioned this asymptotic earlier. By asymptotic, you mean when the data set size is infinite?
Yes. Or yeah. So that's of course an unrealistic condition. So in practice, as I will show, we don't need this. Meaning that we can this kind of method work regardless of how much data you have in calibration set. But indeed, for the theory part, we need like infinite data to have zero like coverage loss. Yeah.
Sure.
Yeah.
Okay.
Yeah. Yeah. So, and another thing to point out, so this is, I didn't show in the slide because I don't want to make the slide too crowded, is that in SPICY, we don't give, at least in this, by that time, we don't give the rate at which this asymptotic coverage is decaying, meaning the coverage gap. But in the earlier work, like in MBPI, we actually give you a rate of how, like the bound on the coverage gap, which is decaying when your sample size, meaning the size of your calibration set, is increasing. So there is indeed a difference, meaning MBPI can give you a tighter, give you more exact quantification at the expense of assuming more. But I think the ideas or technique can carry over. And okay, so after that, I do want to point out several other things. The first is that we do realize that this idea has an interesting connection with this 2023 work. So this work is called Conformal Prediction Beyond Exchangeability. So there the authors consider conformal when your data are not exchangeable. And there they can provide bound on how much you're going to lose in terms of coverage using like total variation between the set of non-conformity scores. And there the solution for in their work is to also weigh your set of non-conformity score. And because we're using quantile random forest, you can, upon more derivation, we can actually show that this result is also a type of weight, where the weights are learned by this quantile random forest. So that is one thing I want to point out, like the connection with existing work. And another thing is that when we first present this work, people were asking us, how do you differ from this 2019 work called conformalized contour regression? I guess a lot of you have seen that because it's a very famous one. And I think one key difference is that they are trying to make an existing contour regression model conformalized, where this contour regression is fitted on your original sequence, X and Y. And in comparison, what we are doing is not fitting this calligraphic Q on your original series, but instead we're fitting it on this set of non-conformity score computed on your calibration set. So that is one difference, or one key difference that I want to point out. And additionally, so I have a single slide to explain how �値is currently being extended for multivariate time series. So here the setup is, suppose we have a vector now. So your YT, so XT can still be any vector because we never restrict that. But here, suppose your YT in the dimensional RP is a vector, and there we are trying to build prediction region. So this region now is a subset of RP rather than an interval because it's a multivariate, and we are also subjecting to the same coverage guarantee. And I think a concrete example of here is, suppose you have different sensors or different stations that we are collecting observation on, and each of this YT will be the observations that you collect at time t from all of those stations. So that is like one of the concrete understanding. And I think besides more technical detail, the key difference between, not key difference, but the key change that we make in order to make this work is how we design the conformity score. So remember previously, maybe I just go back, previously the conformity score is pretty simple, meaning you just take the residual here. So like in univariate case, you just take a residual. But in multivariate case, if you can, of course, still take residual, and I will explain what that type of method relates. But I think we realize that if you not just take residual, but rather take in this form, in this case, ellipsoids, score based on the ellipsoid, there you can actually have very much tighter prediction region than if you use something else. So in case you haven't seen, essentially you just have this, we have a low rank as approximation of your sample covariance of your residuals. And why we have considered low rank is because in some cases, your original covariance matrix might not be, because it's the empirical covariance matrix, it's not the actual covariance matrix. So empirically, that might not be invertible. But if you have the low rank approximation and you consider the pseudo inverse, this is always valid. And there, if you consider inner product with respect to your estimation, you will have still a scalar nonconformity score. So equation 1 still gives you a scalar given each of this multivariate response or feature. And there, given this design of nonconformity score, we are still going to use the existing �値, meaning you fit a set of quantile regression model on each of this nonconformity score, and then you're going to get the set of, you're going to include the region, the set of Y that have low, small conformity score, non-conformity score. Yeah.
Sorry. Could you mention one more time what motivates this choice of conformity score?
Yeah. So the reason being, first there are several things. The first is we of course still want a scalar, right? Because if we have a vector, there taking quantile, etc. for a vector can be very difficult. So that's why we need a scalar, and that's the first thing. And then I think that's a simple thing. And the second thing is we want to jointly capture the dependency among your residual. Because in this case, when it is a vector, it is you can no longer assume them to be independent across each component. So that's the second thing. And I think the last thing is that we also want something that is simple, meaning that there are work that are allow you to consider these two things jointly. But we want something simple to compute. So that's why one way to do is that we build an ellipsoid at each of as each of the confidence region. And in order to define the ellipsoid, you essentially will operate on sample covariance matrix. And in order to make ensure everything is invertible, we consider a low rank approximation with pseudo inverse. So that is like the idea.
All right.
Yeah.
Thank you.
And additional.
Sorry, I think we have a question.
Sure, I can see. So please.
Yeah. I think it's Mohammed Reza. Please unmute and go ahead.
Hi, Chen, it's Reza. I have a quick question. So if on one of your dimensions you have a very weak predictor and your residuals are higher, would that affect the efficiency, the overall efficiency of your model? So let's say you have a very bad model on one of your dimensions, then wouldn't that cause your total efficiency to go down?
Yes, I agree. I think that is yes, because in general we are agnostic to the predictor we are considering. So I agree. If we have a poor prediction along one of the dimension, then indeed, conformal prediction alone will not allow you to alleviate the problem. Yeah, but I do think there are works that try to further operate on your predictor, but I don't think that's the intention I'm trying to do, because I'm more like a post hoc way. Yeah.
I see. Yeah. Thank you.
Yeah. And
so do you have any insights when you compare that scenario with the case that you have? You try to have a vector conformity score compared to the scalar one that you have here. Do you have any insight on that? How would that differentiate when you consider it as a vector or as a scalar?
Yeah, exactly. And that's actually the second bullet I'm going to show.
Okay,
so let me just go there. So in fact, there are a line of work called copula, especially in conformal copula. So there, they actually consider such type of vector case. And without going too detail into copula, you can essentially understand it as also trying to jointly considering everything across your components of the vector. And I would say they have different formulation. So from the formulation point of view, I wouldn't say one is necessarily better than another. Although I do find that when you're doing this equation one, meaning you reduce the vector to a scalar and then operate conformal, that is simpler than you just operate it on the original vector. And then in order to operate that, people wrap the so-called copula around it. So that's one thing, meaning design choice, I think equation one is simpler because using copula is a little more complicated. And the second thing is that, as I will show, empirically, when you do one, it actually also gives you a better performance than suppose you're considering this vector jointly. Yeah. But I would say they're all valuable approaches. I don't think I'm just saying in multivariate case we should just consider this, but rather I think this is a very natural way to do. Yeah, and I think indeed in past work people have considered ellipsoids, but that's not for time series setting, and also so that's why there's a major difference here. Yeah. And if you're interested, so this work, I'm happy to chat more because this is fairly recent in this year, and we're still investigating actively along the line as well. And by the way, all of the code are available. So for all of the work I talked, and in the end, I'll have a conclusion slide, like summarizing everything, and there you can also go to every paper to check code, etc. So I do want, before I present more empirical results, I do want to give a quick summary. So again, the goal is to have uncertain quantification through this construction of interval or region for your response. And I discussed the simple case of having a linear regression where if you have a strong assumption, but you can also give a very precise interval under this assumption. And then I discussed how conformal prediction in a nutshell operates by operating on the set of conformity score or non-conformity score. And then I quickly covered a few lines of work that we considered, where we are extending conformal beyond exchangeable data and specifically for time series. So MBPI in a nutshell have two components. The first is that you try to learn a sample predictor of your F. And the second is that we are trying to update the set of non-conformity score that is computed on the calibration set. So you can understand this as saying, initially, I have my calibration set. And then as I observe more test samples after constructing the intervals, I can update the set of non-conformity score in order to make everything more adaptive and precise. And the second is the so-called spicy, where instead of just using the empirical quantile Q, on this set of non-conformity score, I'm using a calligraphic Q hat, which is a fitted quantile regression model on the same set of non-conformity score. And in that work, we considered quantile random forest as a natural choice. And in extensions later in this presentation, I'll also show some other additional use that we consider. And the last is that in order to make spicy work naturally in multidimensional case, we try to redesign the choice of the non-conformity score so that everything can easily follow. And also empirically, I will show some benefits of doing so. And next, I think a very interesting thing is how the empirical performance, because in many cases, many formulations are valid, but we do want to test or see how well they perform on different situations. So for EMBPI, by the time we have that work, there weren't a lot of paper on, especially for conformal beyond exchangeable data. So that's why when we first have that, the first comparison are against some existing CP method, and some of them have considered IID, but not a lot. And the second is that when we also compare with non-exchangeable, with non-conformal prediction methods that are more traditional, for example, traditional ARIMA or exponential smoothing, etc. And for spicy and multidimensional spicy, definitely by that time, a lot of the conformal prediction for time series have been proposed, a lot of methods there. So that's why for these type of works, we mainly consider the comparison against, especially when comparing with CP, we're comparing the methods that are defined for non-exchangeable data. So we're no longer consider like the naive split conformal for exchangeable data. And the second is that we also compare not just with traditional time series approach, but there are more deep learning based probabilistic forecasting approach, such as deep AR, and also a temporal fusion transformer. So those are two things that we compare as well, and I will show the results.
Sorry, Chen, before talking about this in more detail, can you address another question that we have on the chat? It says Nixla has an implementation of conformal prediction. Can you comment their implementation versus the ENBPI implementation? I think it means, can you compare their implementation?
Did they implement ENBPI? Because I don't know. Did they?
Okay.
Because so the point I have is I do know a couple of packages that have implemented ENBPI, and I will actually, my last summary slide includes them, but I'm not sure whether specific repository have implemented. But I do want to point out some of them implementation, when they implemented, they consulted me. So like, let me check the code. There, I think that's pretty similar to what I have. But I don't think in this specific case, I know the implementation. So I don't know much. Yeah.
Okay. Thank you.
Okay, so the first experimental comparison is ENBPI with a lot of the CP methods. And in this slide, in these tables, I'm trying to highlight the proposed method, which is ENBPI in my case. And I think essentially what we're doing here is that we consider different amount of training data, like 10% or 19% or more. I just have these two examples. And then we're seeing how does this method perform when you have this amount of training data. And why we choose a relatively low ratio is that we're interested in like a long horizon prediction, meaning that after we build this predictor or method, we want to roll it out or test it out on possibly long in the future. That's why we chose a relatively low ratio. And I think the takeaway is that MBPI was always able to reach valid coverage, but comparatively some other method, and again, some of these methods or most of them are not for time series. So that's why this comparison is not 100, or it's not necessarily apple to apple. But at that time, when we compare with these methods, you can see they do lose coverage. And sometimes they can also be narrower, but at the expense of losing coverage. And we do have additional results where in order to make a fair comparison, we're purposely adjusting the significance level for those methods so that every method have about the same target coverage. And then we're looking at that level, how do the widths compare to each other? And I think, although I don't show the table, you can trust my word, which is that even in that situation, when all methods have the same coverage, ENBPI still tend to have a narrower interval. So that's, I think, an interesting part that we observe by that time when we do the comparison. So this table can likely differ, and indeed it will differ when we compare ENBPI with newer conformal prediction for time series.
Sorry, one question about the table. Yep. What was the forecast horizon for these comparisons?
Yeah, forecasting. So there are two things. When we build interval one step at a time. But in terms of how many we are constructing like, suppose you have, suppose your total data set has 1,000 sample. That includes both training and testing. What we did is we used the first like the first 10%, meaning we use the first 100 to build interval for all the method. Well, sorry, not build interval, to train all the method, and then we roll it out or test it out on the rest 900. That's the idea. So that's indeed a very, very long horizon prediction.
So the forecast horizon is 100, but you roll it. It's like rolling forecast.
Yeah, rolling for each. Yes. So we are, of course, if it's an existing CP, meaning like split conformal, it doesn't really matter because it assume every data are exchangeable. So there you can produce as many as you want in a single snapshot. But for like the MBPI, which is trying to update every time, there we do have to do like a one step at each time. Yeah.
Sorry, in this example that you mentioned, dataset has 1,000 rows. Let's say you use the first 100 to train, and then what do you use for calibration?
So that's in fact the part where so I gloss over that part, which is here when you have MBPI, we don't need additional calibration. So that's the design choice that I didn't explain in detail, but I'm happy to chat. So the point I want to make is that 100 point is both training and calibration.
Okay, I see.
Yeah. And then the rest 900 is for testing the coverage.
All right.
And of course, in other situation, we can just you can always vary how many data you have. And conformal in itself doesn't rely on how many sample you have, although our guarantee there are asymptotic. But I think this example at least show that you don't need much, well, very many training points to reach reasonable performance.
Right. Thank you.
Yep. Yes, of course. And another plot is, and again, these are relatively early results. So although we redid those, the method itself is not the newest. So that's why I would say these are helpful results, but not the state of the art. And the second is that we also examine MBPI when you consider rolling coverage. What this means is that instead of computing one number for on all the test points, we're considering how well everything is performing at each time. And also, we are also meaning that this is plotted in this red curve, meaning we're considering at each of the time index, how does the coverage vary? So overall, it can have still marginally, you can still have like a one-minute alpha coverage. But of course, there are variation. So that's why sometimes the curve just move around. And here we don't have guarantee there. So that's why this is more like illustrating how things are changing or behaving. And the data here are like solar radiation. So it's one of the power system application. And yeah, so you can see how things are changing. And sometimes, but one thing I do want to point out that is you can see these intervals do not seem to have much variation across different hours, which is not necessarily a good thing because we do want the interval to be adaptive to like the data intrinsics. And that's indeed a limitation of the MBPI, which I think we will see is partly addressed by SPICY.
Sorry, just looking into the plots in the second row, these are moving averages of the empirical coverage, right? Moving average,
exactly.
Moving average. Okay, and then I note that almost all of the plots in the second row, they start well below the target coverage, meaning that it takes like about 2 months, 2-3 months of data for the empirical coverage to reach the target level.
Yeah, I think in 5 out of 8. Yeah, I think at this hour, like 5 p.m., 12, 1, I think these are not the case, but indeed, for several other cases, that's the case. Yeah.
Yeah, okay.
I agree. Yes. So we don't have explanation there, and there we are more like trying to illustrate how this is behaving. And I'm definitely not saying this is the to-go when we're considering the problem, to-go method. Yeah, but yeah, it's a great observation. Yeah, I agree. And And we also there, I just want to, well, I will just quickly go over. Essentially, we compare with non-CP method like ARIMA, exponential smoothing, etc. And I think the takeaway is similar as before, meaning we have valid coverage at different significance level, and the intervals are relatively narrow or narrowest. And now I do want to point out more interesting things. So this is SPICY, which is one of the more recent work we have. So here I highlight SPICY because that is the method we propose in network. And you can still see, so EMBPI is still compared because that was still one of the relatively new work. And what we are doing here is that we consider 3 data sets. So the wind prediction, electric use prediction, and the same solar prediction. And what we're doing is that we are trying to use, for example, in this case, we're not considering that long horizon because sometimes the baselines, they don't work that well if we have very few training sample. So that's why I remember in this case, we use 80% of the total data for training and calibration, and then we test on the rest 20%. And there you can see that SPICY has the narrowest width in almost all the cases, whereas for other methods like EMBPI, adaptive conformal, or others. So these 3 below SPICY are conformal prediction method, where the last 2, like deep autoregressive and TFT, they are not conformal, but they are very well-known probabilistic forecasting approach. So I use, that's why I'm comparing or benchmarking against all of them. And I think the idea is pretty, well, the takeaway is pretty clear, is that while all of them can have valid coverage, the width of SPICY is the narrowest.
And the width that you are reporting in this table is the average test width, right?
Yep, the average. And I will actually show rolling width as well. So this is the average over, in this case, let's still use the 1000. This will be the average over the 200 test point. And now let's go to the rolling case. So this is the same data set and same setup. The only difference is that we are no longer considering average over all the test index, but rather we plot it over the entire test index computing a rolling fashion. And I think one thing is I think in this case, none of the method is significantly below at the beginning. So I think that's a good thing, because one reason is because we have more training sample in this case. And the second thing is that they have similar variation in terms of rolling coverage, although some might have higher, some have lower, but they generally have similar variation. But if you look at the width, which is on the right column, the black, which is SPICY that we propose, there is very likely to have a very narrow interval, or the narrowest interval than the baselines. And some of them, like adaptive conformal, they decay as you have more sample, but initially can be very wide. I think that is an interesting curve or plot to see as well, like the rolling or instantaneous performance rather than averaging over all the test samples.
Sorry, one other question. All these results are for a single split, right? Meaning that the index that separates test from calibration and trend is the same and a single value.
Exactly,
right?
exactly. I think we did repeat, meaning the curves have confidence band. So I forgot exactly how many. I think we did for 3 repetition, but that's the same for all. So meaning when we do, it's the same for all methods. Yeah, but yes, it's single splits. Yeah.
Do you think it would be possible for different methods to perform differently depending on that splitting index? For example, some methods may perform well with a certain index, while others may perform better for another index.
Definitely. I do think it's the case. Yes, definitely. I don't think so. Based on all of my years of working on these things, I would say I don't think there's a single method that beats other methods in all cases. And indeed, I do think some methods can perform better on certain circumstances. But that requires more domain expertise to diagnose like what is happening and do we need to use. But I agree with you.
And then the other question is that for in the second column, rolling width, what is the dimension there? Is that a dimensionless number?
So in this case, we're still considering univariate. So the width is always for univariate confidence interval.
Sure, but I'm trying to compare the width with the level of the origin, with the level of the series. For example, when you say width is 0.4, what was the what was the signal level itself? Is it 0.4 around the signal that oscillates
That's a good
100 point. Or around 10,
yeah,
for example?
That's a good point. I probably can need to check that in the future.
Okay.
I didn't check that, because when we considering these data sets, we may basically just use them from whatever source we had, and we didn't consider too much. But that's a good point. But I do think it won't be the case where you have the original signal being very different from the scale that you were considering. There's likely a balanced situation. And I think this plot is also interesting, meaning we're considering a multi-step prediction. So in the top row, we are using the same MBPI we had, where when we say 4 steps ahead, essentially it means that at each prediction index, we are not just giving you one prediction interval, but rather we're giving you 4 prediction intervals at the same time. And this is why I said 4 steps ahead. And here you can see when we are doing 1 step ahead, although the intervals are much narrower, they do behave well. Sorry, I wouldn't say although. It's just that the spicy is much narrower. But I think the interesting thing is when you predict further ahead, where it's naturally to believe there are more uncertainty. In this case, spicy width accordingly increase, because when you predict further along, there's just naturally more uncertainty and variation. But if you look at the MBPI, when we predict further ahead, the width actually becomes narrower, which is counterintuitive. And I think that's because when we're building that interval, this interval are very non-adaptive to the behavior of your curve. So that I do want to point out is one limitation of the MBPI, which is it can give you valid coverage, but in general cases, the width can be non-adaptive. And I think this I'll just gloss over. Essentially, we compare other data set, and this is stock data set. And there are some cases where we compare similarly against the baseline, and some cases we compare much better or perform much better. So I do think this is also interesting, and this is part of a requirement of the reviewer when they say there are specific data sets they want to look at. So if any of the audience are interested in testing out this method on stock data, or like in this case, the NASDAQ stock market data, I think you can also consider these. And before I go to extension, I do want to show multidimensional spicy results. So in this case, remember the difference from before is we're no longer building interval on a single dimension, but rather we're considering jointly. And in this case, it's the ellipsoid on the rightmost column. So what I'm plotting here are 3 different ways to consider 2-dimensional observation. And so on the left one is the empirical calculus. So you can see it builds a square, and in general they build rectangle. So I think, but in special cases they build square. And in the middle, for example, it's a spherical region, and on the right is what we propose as this ellipsoid with adaptive radius. So I think this is not trying to so how do you say? This is more like a comparative result, but I'm not trying to say one is necessarily better, because the example are fairly simple. It's only 2 dimensions, but I do want to show the visualization of how in this 2-dimensional case, our multidimensional spice is behaving. So I think the interesting thing is it seems to adapt to how your prediction is behaving, and sometimes it's narrower, sometimes it's wider. And additionally, we did a more comprehensive comparison on these data sets. So these data sets, when we collect them, they have multivariate. They are multivariate by collection. It's more like when we test them previously on spicy, we select specific columns, which are the same for all methods. And what we're doing here is that we're using these original sequences by considering different components. Meaning p = 2 means you have 2 dimensions. You consider 2 time series from 2 locations, where if it's 8, you consider 8. So the y dimension is 8. And in this table, the takeaway is that all methods still seem to behave similarly in terms of coverage, and they actually seem to overcover, at least in most cases. But if you're considering the width, multidimensional SPICY can be significantly narrower when you have higher dimension. And I guess that relates to the design of the score, and also, yeah, I think that's the main reason. The design of the score as well as the use of SPICY on top of it. And for those of you who might be interested, the last two rows are still this probabilistic forecasting approach, like TFT and DeepAR. So you can see this method, they are similar, or at least on similar scale when you're operating on low dimension. But if you're operating on high dimension, they can be, I would say, not comparable in terms of how large the set is, because they're trying to give you interval at each coordinate, and then these interval, they will form a hyperrectangle with very large size if you don't calibrate the size, each interval correctly. So that's, I think, the takeaway. I do know I have a few minutes, so I'm going to the extensions that in case anyone is interested. So the first is an anomaly detection. So this is one of the early work. I think the essential idea is that we can still build this interval. And then if you have observations that lie outside the interval, which should happen with probability alpha, then we will choose them as anomaly. So this workshop paper was essentially considering that, and this was developed by the time we had the MBPI. So I believe the results will be different for SPICY. But essentially is that if you use this formulation for anomaly detection, it can still have fairly decent performance measured in terms of F1 score. So that's one thing. And the second is that this idea can also apply for building a prediction set in classification task, because all the previous case, when we consider the observation, or when we consider target Y, although it can be multivariate, it's always continuous, whereas that's where I assume. But if you have classification task where your Y are labels, there it's no longer reasonable to build interval, but rather we should build set. So that's essentially what we were doing, meaning we combine the idea with different design of the nonconformity score in order to build prediction sets, and then evaluate on different significance level to show the performance. And the last several collaborations that I'm not the leading author, but I collaborated on are, we try to further extend SPICY with different approaches. For example, remember I said I use quantile random forest as the predictor of the quantiles of your residuals. And then we later on explore two additional choice. Rather than QRF, quantile random forest, we consider kernel regression. And the reason is that there we can have tighter non-asymptotic gap bound. And the second, more recently, we consider using transformer rather than QRF to build these quantile, because in some cases when you have long dependency, this transformer can help you capture this long-term dependency better. So those two works are still ongoing. They are not published yet, but happy to chat more or refer you to this work if you're interested. Yeah, so I think I'll just conclude by saying conformal prediction offer both distribution-free and model-free UQ, and with guarantee on the coverage. And in our work, we consider three approaches. I would not reiterate, but just these three approaches are what we have been considering and actively developing. And the last is, as I said, I do know there are several public packages that have implemented EMBPI, and some of them I already looked into, because then when they were implementing, they consulted me, but some of them are independent, so I'm not sure how exact they are with respect to my original. And lastly, these three QR code, if you want to scan, you can directly go and see the original paper or the published version. Yeah, thank you.
Well, thank you so much, Chen, for this great presentation. I have one other question.
Yep.
You mentioned
just getting some water. Please ask.
Yeah, sure. So you mentioned that SPICY has asymptotic valid conditional coverage. Is that right?
Yeah.
What do you mean by conditional coverage there?
Yeah. So the conditional is, I just go to the equation. Oh. So this is marginal, right? You are not
right.
So the conditional is I condition on the specific value of your x.
Okay. But that
so
is okay. That is interesting because even the original conformal prediction does not have a valid conditional coverage. when the data set is small.
Yeah. So
But
that's
here,
why I think you need more additional assumption. Yeah, you need additional assumption to do that as well.
Right. Okay.
Yeah. So I see your point. I think for audience, sorry to interrupt you because I don't know if others have questions. So that's why I want to address this quickly. I think Rina Barber, they had a work called essentially saying conditional coverage is impossible even for exchangeable data. So I think that's why if you don't have additional assumption, which is presented in �値 in as one of the example, it's never possible to do that. So that's, I would say, the guarantees are not distribution free. Sorry, are not distribution free. They are distribution free, but not dependency free. I do have to assume some assumption on dependency, not distribution.
Have you seen this? Well, I see that there are no more questions, so I will.
Sure.
I will ask another one. Have you seen about conditional coverage? Have you seen this, like the original works on like 2-parameter coverage validity definition, where you say that I would like the coverage rate to be, for example, 90%, but because it's fixed on a calibration set, it's conditioned on a calibration set, I'm gonna tolerate 10%, for example, of violations in that requirement. So when you define coverage like that, 2-parameter coverage, then that definition of coverage is valid even when you condition on a specific data set.
Yeah, that's a great point. Yes. I personally don't work on that, but I do know. I do know that type of work. Yes, exactly. Yeah, that's a good point. Yes.
All right. Well, I think we don't have any other questions. So I want to thank you again, Chen, for this great presentation. And I want to highlight again that the recording will be available on the channel for those who may want to watch this seminar again. With that, I think we can end the call. Thank you, Chen, again.
Thank you very much.
Yeah.
Thank you.
Bye.
Bye. Thanks.